This unit 2 structure of atom has been divided into two parts, and here is part 1.
Hello everyone, welcome to my audiobook, and today's lesson is from Ncert Chemistry Part 1, Class 11, Unit 2, Structure of Atom. So let's start. First let us see the objectives of this unit. After studying this unit, you will be able to know about the discovery of electron, proton and neutron and their characteristics. Describe Thomson, Rutherford and Bohr atomic models. Understand the important features of the quantum mechanical model of atom. Understand nature of electromagnetic radiation and Planck's quantum theory. Explain the photoelectric effect and describe features of atomic spectra. State the de Broglie relation and Heisenberg uncertainty principle. Define an atomic orbital in terms of quantum numbers. State of Bohr principle, Pauli exclusion principle and Hund's rule of maximum multiplicity, and write the electronic configurations of atoms. So these are the objectives. So let's start now. The rich diversity of chemical behavior of different elements can be traced to the differences in the internal structure of atoms of these elements. The existence of atoms has been proposed since the time of early Indian and Greek philosophers, 400 BC, who were of the view that atoms are the fundamental building blocks of matter. According to them, the continued subdivisions of matter would ultimately yield atoms which would not be further divisible. The word atom has been derived from the Greek word atomio, which means uncut-able or non-divisible. These earlier ideas were more speculations and there was no way to test them experimentally. These ideas remained dormant for a very long time and were revived again by scientists in the 19th century. The atomic theory of matter was first proposed on a firm scientific basis by John Dalton, a British school teacher in 1808. His theory, called Dalton's atomic theory, regarded the atom as the ultimate particle of matter. Dalton's atomic theory was able to explain the law of conservation of mass, law of constant composition, and law of multiple proportion very successfully. However, it failed to explain the results of many experiments. For example, it was known that the substances like glass or ebonite, when rubbed with silk or fur get electrically charged. In this unit, we start with the experimental observations made by scientists towards the end of 19th and beginning of 20th century. These established that atoms are made of subatomic particles, that is, electrons, protons and neutrons, a concept very different from that of Dalton. Next, discovery of subatomic particles. An insight into the structure of atom was obtained from the experiments on electrical discharge through gases. Before we discuss these results, we need to keep in mind a basic rule regarding the behavior of charged particles. Like charges repel each other and unlike charges attract each other. Next, discovery of electron. In 1830, Michael Faraday showed that if electricity is passed through a solution of an electrolyte, chemical reactions occurred at the electrodes, which resulted in the liberation and deposition of matter at the electrodes. He formulated certain laws which you will study in class 12. These results suggested the particulate nature of electricity. In mid-1850s, many scientists, mainly Faraday, began to study electrical discharge in partially evacuated tubes known as cathode ray discharge tubes. It is depicted in figure 2.1. A cathode ray tube is made of glass containing two thin pieces of metal called electrodes sealed in it. The electrical discharge through the gases could be observed only at very low pressure and at very high voltages. The pressure of different gases could be adjusted by evacuation of the glass tubes. When sufficiently high voltage is applied across the electrodes, current starts flowing through a stream of particles moving in the tube from the negative electrode, that is cathode, to the positive electrode, that is anode. These were called cathode rays or cathode ray particles. The flow of current from cathode to anode was further checked by making a hole in the anode and coating the tube behind anode with phosphorescent material zinc sulfide. When these rays, after passing through anode, strike the zinc sulfide coating, a bright spot is developed on the coating. Figure 2.1b. These figures I will be providing at the end of this audiobook. You can check it out. 2.1a and 2.1b. Next, the results of these experiments are summarized below. First point, the cathode ray starts from cathode and move towards the anode. Second point, these rays themselves are not visible, but their behavior can be observed with the help of certain kind of materials, fluorescent or phosphorescent, which glow when hit by them. Television picture tubes or cathode ray tubes and television pictures result due to fluorescence on the television screen coated with certain fluorescent or phosphorescent material. Third point, in the absence of electrical or magnetic field, these rays travel in straight lines. Figure 2.2. Next, fourth point. In the presence of electrical or magnetic field, the behavior of cathode rays are similar to that expected from negatively charged particles, suggesting that the cathode rays consist of negatively charged particles called electrons. Next, fifth point. The characteristics of cathode rays, that is electrons, do not depend upon the material of electrodes and the nature of the gas present in the cathode ray tube. Thus, we can conclude that electrons are basic constituent of all the atoms. Next, charge to mass ratio of electron. In 1897, British physicist J. Thomson measured the ratio of electrical charge E to the mass of electron Me by using the cathode ray tube and applying electrical and magnetic field perpendicular to each other as well as to the path of electrons. Figure 2.2. When only electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A. Figure 2.2. Similarly, when only magnetic field is applied, electron strikes the cathode ray tube at point C. By carefully balancing the electrical and magnetic field strength, it is possible to bring back the electron to the path which is followed in the absence of electric or magnetic field, and they hit the screen at point B. Thomson argued that the amount of deviation of the particles from their path in the presence of electrical or magnetic field depends upon, first point, the magnitude of the negative charge on the particle. Greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic field, and thus greater is the deflection. Second point, the mass of the particle, lighter the particle, greater the deflection. Third point, the strength of the electrical or magnetic field, the deflection of electrons from its original path increases with the increase in the voltage across the electrodes or the strength of the magnetic field. By carrying out accurate measurements on the amount of deflections observed by the electrons on the electric field strength or magnetic field strength, the Thomson was able to determine the value of E by Me as E by Me equals to 1.758820 into 10 to the power of 11 coulomb per kg, where Me is the mass of the electron in kg and E is the magnitude of the charge on the electron in coulomb, that is C. Since electrons are negatively charged, the charge on electron is minus E. Next, 2.1.3, charge on the electron. R. A. Millikan, 1868 to 1953, devised a method known as oil drop experiment, 1906 to 14, to determine the charge on the electrons. He found the charge on the electron to be minus 1.6 into 10 to the power of minus 19 coulombs. The present accepted value of electrical charge is minus 1.602176 into 10 to the power of minus 19 coulomb. The mass of the electron Me was determined by combining these results with Thomson value of E by Me ratio. Me equals to E by E per Me, which gives to 9.1094 into 10 to the power of minus 31 kg. So here they have given figure 2.2, the apparatus to determine the charge to the mass ratio of electron. This I will be providing, you can check it out. Next, 2.1.4, discovery of protons and neutrons. Electrical discharge carried out in the modified cathode ray tube led to the discovery of canal rays carrying positively charged particles. The characteristics of these positively charged particles are listed below. First point. Unlike cathode rays, mass of positively charged particles depend upon the nature of gas present in the cathode ray tube. These are simply the positively charged gaseous ions. Second point. The charge to mass ratio of the particles depends on the gas from which these originate. Next, third point. Some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. Next, fourth point. The behavior of these particles in the magnetic or electrical field is opposite to that observed for electron or cathode rays. The smallest and lightest positive ion was obtained from hydrogen and was called proton. This positively charged particle was characterized in 1919. Later, a need was felt for the presence of electrically neutral particle as one of the constituent of atom. These particles were discovered by Chadwick 1932 by bombarding a thin sheet of beryllium by alpha particles. When electrically neutral particles having a mass slightly greater than that of protons were emitted, he named these particles as neutrons. The important properties of all these fundamental particles are given in table 2.1. Next is atomic models. Observations obtained from the experiments mentioned in the previous sections have suggested that Dalton's indivisible atom is composed of subatomic particles carrying positive and negative charges. The major problems before the scientists after the discovery of subatomic particles were: first one, to account for the stability of atom; second one, to compare the behavior of elements in terms of both physical and chemical properties; and next, to explain the formation of different kinds of molecules by the combination of different atoms; and next point, to understand the origin and nature of the characteristics of electromagnetic radiation observed or emitted by atoms. So in figure 2.3, the Millikan oil drop apparatus for measuring charge E in chamber. The forces acting on oil drop are gravitational, electrostatic due to electric field, and a viscous drag force when the oil drop is moving. So this is given, the figure is given, that is the Millikan's oil drop method. Okay, so let's have a look into this Millikan's oil drop method. In this method, oil droplets in the form of mist produced by the atomizer were allowed to enter through a tiny hole in the upper plate of electrical condenser. The downward motion of these droplets was viewed through the telescope equipped with a micrometer eyepiece. By measuring the rate of the fall of these droplets, Millikan was able to measure the mass of oil droplets. The air inside the chamber was ionized by passing a beam of X-rays through it. The electrical charge on these oil droplets were acquired by collisions with gaseous ions. The fall of these charged oil droplets can be retarded, accelerated, or made stationary depending upon the charge on the droplets and the polarity and strength of the voltage applied to the plate. By carefully measuring the effects of electrical field strength on the motion of oil droplets, Millikan concluded that the magnitude of electrical charge Q on the droplets is always an integral multiple of the electrical charge E, that is Q equals to Ne, where N equals to 1, 2, 3 goes on. And here is the figure they have given. I will be providing, you can check it out. Next is the table 2.1, properties of fundamental particles. Different atomic models were proposed to explain the distributions of these charged particles in an atom. Although some of these models were not able to explain the stability of atoms, two of these models, one proposed by J.J. Thomson and the other proposed by Ernest Rutherford, are discussed below. First one, Thomson model of atoms. J.J. Thomson in 1898 proposed that an atom possesses a spherical shape, radius approximately 10 to the power of minus 10 m, in which the positive charge is uniformly distributed. The electrons are embedded into it in such a manner as to give the most stable electrostatic arrangement, figure 2.4. Many different names are given to this model, for example, plum pudding, raisin pudding, or watermelon. This model can be visualized as a pudding or watermelon or positive charge with plums or seeds, that is electrons embedded into it. An important feature of this model is that the mass of the atom is assumed to be uniformly distributed over the atom. Although this model was able to explain the overall neutrality of the atom but was not consistent with the results of later experiments. Thomson was awarded Nobel Prize for Physics in 1906 for his theoretical and experimental investigations on the conduction of electricity by gases. Okay, so here is a green box is there. So let's see what's there in it. In the latter half of the 19th century, different kinds of rays were discovered, besides those mentioned earlier. Wilhelm Röntgen, 1845 to 1923, in 1895 showed that when electrons strike a material in the cathode ray tubes, produce rays which can cause fluorescence in the fluorescent materials placed outside the cathode ray tubes. Since Röntgen did not know the nature of the radiation, he named them X-rays, and the name is still carried on. It was noticed that X-rays are produced effectively when electrons strike the dense metal anode called targets. These are not deflected by the electric and magnetic fields and have a very high penetrating power through the matter, and that is the reason that these rays are used to study the interior of the objects. These rays are of very short wavelength and possess electromagnetic characters. Henry Becquerel, 1852 to 1908, observed that there are certain elements which emit radiation on their own and named this phenomenon as radioactivity, and the elements known as radioactive elements. This field was developed by Marie Curie, Pierre Curie, Rutherford, and Frederick Soddy. It was observed that three kinds of rays, that is alpha, beta, and gamma rays, are emitted. Rutherford found that alpha rays consist of high energy particles carrying 2 units of positive charge and 4 units of atomic mass. He concluded that alpha particles are helium nuclei, as when alpha particles combined with 2 electrons yielded helium gas. Beta rays are negatively charged particles similar to electrons. The gamma rays are high energy radiations like X-rays are neutral in nature and do not consist of particles. As regards penetrating power, alpha particles are the least, followed by beta rays, 100 times that of alpha particles, and gamma rays 1000 times of that of alpha particles. Next is Rutherford's nuclear model of atom. Rutherford and his students Hans Geiger and Ernest Madsen bombarded very thin gold foil with alpha particles. Rutherford's famous alpha particle scattering experiment is represented in figure 2.5. A stream of high energy alpha particles from a radioactive source was directed at a thin foil, thickness 100 nanometers, of gold metal. The thin gold foil has a circular fluorescent zinc sulfide screen around it. Whenever alpha particles struck the screen, a tiny flash of light was produced at that point. The results of scattering experiment were quite unexpected. According to Thomson's model of atom, the mass of each gold atom in the foil should have been spread evenly over the entire atom, and alpha particles had enough energy to pass directly through such a uniform distribution of mass. It was expected that the particles would slow down and change directions only by small angles as they passed through the foil. It was observed that, so these are given in the form of points. Let's see. First point, most of the alpha particles passed through the gold foil undeflected. Second point, a small fraction of the alpha particles was deflected by small angles. Third point, a very few alpha particles, 1 in 20,000, bounced back, that is, were deflected by nearly 180 degrees. On the basis of the observations, Rutherford drew the following conclusions regarding the structure of atom. First point, most of the space in the atom is empty as most of the alpha particles passed through the foil undeflected. Second point, a few positively charged alpha particles were deflected. The deflection must be due to enormous repulsive force, showing that the positive charge of the atom is not spread throughout the atom as Thomson has presumed. The positive charge has to be concentrated in a very small volume that repelled and deflected the positively charged alpha particles. Third point, calculations by Rutherford showed that the volume occupied by the nucleus is negligibly small as compared to the total volume of the atom. The radius of the atom is about 10 to the power of minus 10 meters, while that of nucleus is 10 to the power of minus 15 m. One can appreciate this difference in size by realizing that if a cricket ball represents a nucleus, then the radius of atom would be about 5 kilometers. On the basis of above observations and conclusions, Rutherford proposed the nuclear model of atom. According to the model, first point, the positive charge and most of the mass of the atom was densely concentrated in extremely small region. This very small portion of the atom was called nucleus by Rutherford. Second point, the nucleus is surrounded by electrons that move around the nucleus with a very high speed in circular paths called orbits. Thus, Rutherford's model of atom resembles the solar system, in which the nucleus plays the role of sun and the electrons that of revolving planets. Third point, electrons and the nucleus are held together by electrostatic forces of attraction. Next is atomic number and mass number. The presence of positive charge on the nucleus is due to the protons in the nucleus. As established earlier, the charge on the proton is equal but opposite to that of electron. The number of protons present in the nucleus is equal to atomic number Z. For example, the number of protons in the hydrogen nucleus is 1. In sodium atom, it is 11. Therefore, their atomic numbers are 1 and 11 respectively. In order to keep the electrical neutrality, the number of electrons in an atom is equal to the number of protons, atomic number Z. For example, number of electrons in hydrogen atom and sodium atom are 1 and 11 respectively. Atomic number represented by Z equals to number of protons in the nucleus of an atom equals to number of electrons in a neutral atom. While the positive charge of the nucleus is due to protons, the mass of the nucleus due to protons and neutrons. As discussed earlier, protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number, represented by capital A of the atom. Mass number A equals to number of protons Z plus number of neutrons N. Next, isobars and isotopes. The composition of any atom can be represented by using the normal element symbol X with superscript on the left hand side as the atomic mass number A and subscript Z on the left hand side as the atomic number. Isobars are the atoms with same mass number but different atomic number, for example 14C6 and 14N7. On the other hand, atoms with identical atomic number but different atomic mass number are known as isotopes. In other words, according to equation 2.4, it is evident that difference between the isotopes is due to the presence of different number of neutrons present in the nucleus. For example, considering of hydrogen atom again, 99.985% of hydrogen atoms contain only one proton. This isotope is called protium 1H1. Rest of the percentage of hydrogen atom contains two other isotopes. The one containing one proton and one neutron is called deuterium 2D1. 0.015%, and the other one possessing one proton and two neutrons is called tritium 3T1. The latter isotope is found in trace amounts on the earth. Other examples of commonly occurring isotopes are carbon atoms containing 6, 7 and 8 neutrons besides 6 protons, means 12C6, 13C6, 14C6. Chlorine atoms containing 18 and 20 neutrons besides 17 protons. Lastly, an important point to mention regarding isotopes is that chemical properties of atoms are controlled by the number of electrons, which are determined by the number of protons in the nucleus. Number of neutrons present in the nucleus have very little effect on the chemical properties of an element. Therefore, all isotopes of a given element show same chemical behavior. So they have given a problem here in the box. I will be providing that to you. Next, drawbacks of Rutherford model. As you have learnt about, Rutherford nuclear model of an atom is like a small scale solar system with the nucleus playing the role of the massive sun and the electrons being similar to the lighter planets. When classical mechanics is applied to the solar system, it shows that planets describe well-defined orbits around the sun. The gravitational force between the planets is given by the expression G m1 m2 by r2, where m1 and m2 are the masses, r is the distance of separation of the masses, and g is the gravitational constant. The theory can also calculate precisely the planetary orbits, and these are in agreement with the experimental measurements. The similarity between the solar system and the nuclear model suggests that electrons should move around the nucleus in well-defined orbits. Further, the Coulomb force K q1 q2 by r square, where q1 and q2 are the charges, r is the distance of separation of charges, and k is the proportionality constant between the electron and the nucleus, is mathematically similar to the gravitational force. However, when a body is moving in an orbit, it undergoes acceleration even if it is moving with a constant speed in an orbit because of changing direction. So, an electron in the nuclear model describing planet-like orbits is under acceleration. According to the electromagnetic theory of Maxwell, charged particles when accelerated should emit electromagnetic radiation. This feature does not exist for planets since they are uncharged. Therefore, an electron in an orbit will emit radiation. The energy carried by radiation comes from electronic motion. The orbit will thus continue to shrink. Calculations show that it should take an electron only 10 to the power of minus 8 seconds to spiral into the nucleus. But this does not happen. Thus, the Rutherford model cannot explain the stability of an atom. If the motion of an electron is described on the basis of the classical mechanics and electromagnetic theory, you may ask that since the motion of electrons in orbits is leading to the instability of the atom, then why not consider electrons as stationary around the nucleus? If the electrons were stationary, electrostatic attraction between the dense nucleus and the electrons would pull the electrons toward the nucleus to form a miniature version of Thomson's model of atom. Another serious drawback of the Rutherford model is that it says nothing about distribution of the electrons around the nucleus and the energies of these electrons. Next is developments leading to the Bohr's model of atom. Historically, results observed from the studies of interactions of radiations with matter have provided immense information regarding the structure of atoms and molecules. Niels Bohr utilized these results to improve upon the model proposed by Rutherford. Two developments played a major role in the formulation of Bohr's model of atom. These were, first one, dual character of the electromagnetic radiation, which means that radiations possess both wave-like and particle-like properties, and second one, experimental results regarding atomic spectra. First, we will discuss about the dual nature of electromagnetic radiations. Experimental results regarding atomic spectra will be discussed in section 2.4. Next, wave nature of electromagnetic radiation. In the mid-19th century, physicists actively studied absorption and emission of radiation by heated objects. These are called thermal radiations. They try to find out of what the thermal radiation is made. It is now a well-known fact that thermal radiations consist of electromagnetic waves of various frequencies or wavelengths. It is based on a number of modern concepts which were unknown in the mid-19th century. First, active study of thermal radiation laws occurred in the 1850s, and the theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by James Clerk Maxwell, which was experimentally confirmed later by Heinrich Hertz. Here we will learn some facts about electromagnetic radiations. James Maxwell, 1870, was the first to give a comprehensive explanation about interaction between the charged bodies and the behavior of electrical and magnetical fields on macroscopic level. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiation. Light is a form of radiation known from early days, and speculation about its nature dates back to remote ancient times. In earlier days, Newton, light was supposed to be made of particles, corpuscles. It was only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electric and magnetic character. Figure 2.6. Although electromagnetic wave motion is complex in nature, we will consider here only a few simple properties. First one, the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave. Simplified picture of electromagnetic wave is shown in figure 2.6. These figures I will be providing at the end of this audiobook. You can check it out. Next, second point is, unlike sound waves or waves produced in water, electromagnetic waves do not require medium and can move in vacuum. Third point, it is now well established that there are many types of electromagnetic radiations which differ from one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Figure 2.7. Different regions of the spectrum are identified by different names. Some examples are radio frequency region around 10 to the power of 6 Hz used for broadcasting. Microwave region around 10 to the power of 10 Hz used for radar. Infrared region around 10 to the power of 13 Hz used for heating. Ultraviolet region around 10 to the power of 16 Hz, a component of sun's radiation. The small portion around 10 to the power of 15 Hz is what is ordinarily called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiation. Next, fourth point. Different kinds of units are used to represent electromagnetic radiation. These radiations are characterized by the properties, namely frequency and wavelength. The SI unit for frequency is Hertz. After Heinrich Hertz, it is defined as the number of waves that pass a given point in 1 second. Wavelength should have the units of length, and as you know that SI units of length is meter. Since electromagnetic radiation consists of different kinds of waves of much smaller wavelengths, smaller units are used. Figure 2.7 shows various types of electromagnetic radiations which differ from one another in wavelengths and frequencies. In vacuum, all types of electromagnetic radiations, regardless of wavelength, travel at the same speed, that is 3.0 into 10 to the power of 8 meters per second. This is called speed of light and is given by the symbol c. The frequency, wavelength and velocity of light are related by the equation that is given in 2.5. The other commonly used quantity, especially in spectroscopy, is the wave number. It is defined as a number of wavelengths per unit length. Its units are reciprocal of wavelength unit, that is per meter. However, commonly used unit is per centimeter, not SI unit. So next is they have given problems 2.3, 2.4, 2.5. Okay, next these I will provide at the end of the lesson. You can check it out. Next is particle nature of electromagnetic radiation, Planck's quantum theory. Some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. However, following are some of the observations which could not be explained with the help of even the electromagnetic theory of 19th century physics, known as classical physics. First point, the nature of emission of radiation from hot bodies, black body radiation. Second point, ejection of electrons from metal surface when radiation strikes it. Photoelectric effect. Next, third point, variation of heat capacity of solids as a function of temperature. Next, fourth point, line spectra of atoms with special reference to hydrogen. These phenomena indicate that the system can take energy only in discrete amounts. All possible energies cannot be taken up or radiated. It is noteworthy that the first concrete explanation for the phenomenon of the black body radiation mentioned above was given by Max Planck in 1900. Let us first try to understand this phenomenon which is given below. Hot objects emit electromagnetic radiations over a wide range of wavelengths. At high temperatures, an appreciable proportion of radiation is in the visible region of the spectrum. As the temperature is raised, a higher proportion of short wavelength blue light is generated. For example, when an iron rod is heated in a furnace, it first turns to dull red and then progressively becomes more and more red as the temperature increases. As this is heated further, the radiation emitted becomes white and then becomes blue as the temperature becomes very high. This means that red radiation is most intense at a particular temperature and the blue radiation is more intense at another temperature. This means intensities of radiations of different wavelengths emitted by hot body depend upon its temperature. By late 1850s, it was known that objects made of different material and kept at different temperatures emit different amount of radiation. Also, when the surface of an object is irradiated with light electromagnetic radiation, a part of the radiant energy is generally reflected. As such, a part is observed and a part of it is transmitted. The reason for incomplete absorption is that ordinary objects are, as a rule, imperfect absorbers of radiation. An ideal body which emits and absorbs radiation of all frequencies uniformly is called a black body, and the radiation emitted by such a body is called black body radiation. In practice, no such body exists. Carbon black approximates fairly closely to black body. A good physical approximation to a black body is a cavity with a tiny hole which has no other opening. Any ray entering the hole will be reflected by the cavity walls and will be eventually absorbed by the walls. A black body is also perfect radiator of radiant energy. Furthermore, a black body is in thermal equilibrium with its surroundings. It radiates same amount of energy per unit area as it absorbs from its surroundings in any given time. The amount of light emitted, intensity of radiation from a black body and its spectral distribution depends only on its temperature. At a given temperature, intensity of radiation emitted increases with the increase of wavelength, reaches a maximum value at a given wavelength and then starts decreasing with further increase of wavelength as shown in figure 2.8. Also, as the temperature increases, maximum of the curve shifts to short wavelength. Several attempts were made to predict the intensity of radiation as a function of wavelength, but the results of the above experiment could not be explained satisfactorily on the basis of the wave theory of light. Max Planck arrived at a satisfactory relationship by making an assumption that absorption and emission of radiation arises from oscillator, that is atoms in the wall of black body. Their frequency of oscillation is changed by interaction with oscillators of electromagnetic radiation. Planck assumed that radiation could be subdivided into discrete chunks of energy. He suggested that atoms and molecules could emit or absorb energy only in discrete quantities and not in a continuous manner. He gave the name quantum to the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. The energy E of a quantum of radiation is proportional to its frequency and is expressed by equation 2.6 equals to h mu. The proportionality constant h is known as Planck's constant and has the value 6.626 into 10 to the power of minus 34 joules per second. With this theory, Planck was able to explain the distribution of intensity in the radiation from black body as a function of frequency or wavelength at different temperatures. Quantization has been compared to standing on a staircase. A person can stand on any step of a staircase, but it is not possible for him or her to stand in between the two steps. The energy can take any one of the values from the following set, but cannot take on any values between them. Photoelectric effect. In 1887, H. Hertz performed a very interesting experiment in which electrons or electric current were ejected when certain metals, for example potassium, rubidium, cesium, etc. were exposed to a beam of light as shown in figure 2.9. The phenomenon is called photoelectric effect. The results observed in these experiments were: first point, the electrons are ejected from the metal surface as soon as the beam of light strikes the surface. That is, there is no time lag between the striking of light beam and the ejection of electrons from the metal surface. Second point, the number of electrons ejected is proportional to the intensity or brightness of light. Next, third point, for each metal there is a characteristic minimum frequency V0, also known as threshold frequency, below which photoelectric effect is not observed. At a frequency V greater than V0, the ejected electrons come out with certain kinetic energy. The kinetic energies of these electrons increase with the increase of frequency of the light used. All the above results could not be explained on the basis of laws of classical physics. According to latter, the energy content of the beam of light depends upon the brightness of the light. In other words, number of electrons ejected and kinetic energy associated with them should depend on the brightness of light. It has been observed that though the number of electrons ejected does depend upon the brightness of light, the kinetic energy of the ejected electrons does not. For example, red light V equal to 4.3 to 4.6 into 10 to the power 14 Hertz of any brightness or intensity may shine on a piece of potassium metal for hours, but no photoelectrons are ejected. But as soon as even a very weak yellow light V equals to 5.1 to minus 5.2 into 10 to the power of 14 Hertz shines on the potassium metal, the photoelectric effect is observed. The threshold frequency for potassium metal is 5.0 into 10 to the power of 14 Hertz. Einstein in 1905 was able to explain the photoelectric effect using Planck's quantum theory of electromagnetic radiation as a starting point. So here is a box about Albert Einstein. Let's see. Albert Einstein, a German-born American physicist, is regarded by many as one of the two great physicists the world has known. The other is Isaac Newton. His three research papers on special relativity, Brownian motion and the photoelectric effect, which he published in 1905 while he was employed as a technical assistant in a Swiss patent office in Bern, have profoundly influenced the development of physics. He received the Nobel Prize in Physics in 1921 for his explanation of the photoelectric effect. So Albert Einstein, 1879 to 1955. Shining a beam of light on to a metal surface can therefore be viewed as shooting a beam of particles, the photons. When a photon of sufficient energy strikes an electron in an atom of the metal, it transfers its energy instantaneously to the electron during the collision, and the electron is ejected without any time lag or delay. Greater the energy possessed by the photon, greater will be the transfer of energy to the electron and greater the kinetic energy of the ejected electron. In other words, kinetic energy of the ejected electron is proportional to the frequency of the electromagnetic radiation. Since the striking photon has energy equal to h mu and the minimum energy required to eject the electron is hv0, also called work function w0, then the difference in energy is transferred as the kinetic energy of the photoelectron. Following the conservation of energy principle, the kinetic energy of the ejected electron is given by the equation h v equals to hv0 plus 1 by 2 mev square, where me is the mass of the electron and v is the velocity associated with the ejected electron. Lastly, a more intense beam of light consists of larger number of photons. Consequently, the number of electrons ejected is also larger as compared to that in an experiment in which a beam of weaker intensity of light is employed. Next, dual behavior of electromagnetic radiation. The particle nature of light posed a dilemma for scientists. On the one hand, it could explain the black body radiation and photoelectric effect satisfactorily, but on the other hand, it was not consistent with the known wave behavior of light, which could account for the phenomenon of interference and diffraction. The only way to resolve the dilemma was to accept the idea that light possesses both particle and wave-like properties, that is, light has dual behavior. Depending on the experiment, we find that light behaves either as a wave or as a stream of particles. Whenever radiation interacts with matter, it displays particle-like properties in contrast to the wave-like properties, interference and diffraction, which it exhibits when it propagates. This concept was totally aligned to the way the scientists thought about matter and radiation, and it took them a long time to become convinced of its validity. It turns out as You shall see later that some microscopic particles like electrons also exhibit this wave particle duality. Next, problems 2.6, 2.7 up to 2.9 were given. Okay, next. Evidence for the quantized electronic energy levels, atomic spectra. The speed of light depends upon the nature of medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelength bends more than one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out into a series of colored bands called spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.50 into 10 to the power of 14 Hz to red at 4.10 to the power of 14 Hz. Such a spectrum is called continuous spectrum. Continuous because violet merges into blue, blue into green, and so on. Similar spectrum is produced when a rainbow forms in the sky. Remember that visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter, atoms and molecules may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state. For returning to their normal, more stable, lower energy state, the atoms and molecules emit radiations in various regions of the electromagnetic spectrum. Next is emission and absorption spectra. The spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. Atoms, molecules, or ions that have absorbed radiation are said to be excited. To produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength or frequency of the radiation emitted as the sample gives up the absorbed energy is recorded. An absorption spectrum is like the photographic negative of an emission spectrum. A continuum of radiation is passed through a sample which absorbs radiation of certain wavelengths. The missing wavelength, which corresponds to the radiation absorbed by the matter, leave dark spaces in the bright continuous spectrum. The study of emission or absorption spectra is referred to as spectroscopy. The spectrum of the visible light, as discussed above, was continuous as all wavelengths, red to violet, of the visible light are represented in the spectra. The emission spectra of atoms in the gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelengths with dark spaces between them. Such spectra are called line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Line emission spectra are of great interest in the study of electronic structure. Each element has a unique line emission spectrum. The characteristic lines in atomic spectra can be used in chemical analysis to identify unknown atoms in the same way as fingerprints are used to identify people. The exact matching of lines of the emission spectrum of the atoms of a known element with the lines from an unknown sample quickly establishes the identity of the latter. German chemist Robert Bunsen, 1811 to 1899, was one of the first investigators to use line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium, and scandium were discovered when their minerals were analyzed by spectroscopic methods. The element helium was discovered in the sun by spectroscopic method. Next, line spectrum of hydrogen. When an electric discharge is passed through gaseous hydrogen, the H2 molecules dissociate and the energetically excited hydrogen atoms produced emit electromagnetic radiation of discrete frequencies. The hydrogen spectrum consists of several series of lines named after their discoverers. Balmer showed in 1885 on the basis of experimental observations that if spectral lines are expressed in terms of wave number, then the visible lines of the hydrogen spectrum obey the following formula. Wave number equals to 109 109677 in brackets 1 by 2 square minus 1 by n square per centimeter, where n is an integer equal to or greater than 3. The series of the lines described by this formula are called Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. The Swedish spectroscopist Johannes Rydberg noted that all series of lines in the hydrogen spectrum could be described by the following expression. Wave number equals to 109.677 in brackets 1 by n1 square minus 1 by n2 square per centimeter, where n1 equals to 1, 2, etc. n2 means n1 plus 1, n1 plus 2, etc. It goes on. The value 109677 per centimeter is called the Rydberg constant for hydrogen. The first 5 series of lines that correspond to N1 equals to 1, 2, 3, 4, 5 are known as Lyman, Balmer, Paschen, Brackett and Pfund series respectively. Table 2.3 shows these series of transitions in the hydrogen spectrum. Figure 2.11 shows the Lyman, Balmer and Paschen series of transitions for a hydrogen atom. I will be providing all these pictures, all these figures at the end of this audiobook. You can check it out. All the elements, hydrogen atom has a simplest line spectrum. Line spectrum becomes more and more complex for heavier atom. There are, however, certain features which are common to all line spectra. That is, first one, line spectrum of element is unique, and the second one, there is regularity in the line spectrum of each element. The questions which arise are, what are the reasons for these similarities? Is it something to do with the electronic structure of atoms? These are the questions need to be answered. We shall find later that the answers to these questions provide the key in understanding electronic structure of these elements. Next, Bohr's model for hydrogen atom. Niels Bohr, 1913, was the first to explain quantitatively the general features of the structure of hydrogen atom and its spectrum. He used Planck's concept of quantization of energy. Though the theory is not the modern quantum mechanics, it can still be used to rationalize many points in the atomic structure and spectrum. Bohr's model for hydrogen atom is based on the following postulates. First point, the electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits, stationary states or allowed energy states. These orbits are arranged concentrically around the nucleus. Second point, the energy of an electron in the orbit does not change with time. However, the electron will move from a lower stationary state to higher stationary state when required amount of energy is observed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. The energy change does not take place in a continuous manner. Third point, the frequency of radiation observed or emitted when transition occurs between two stationary states that differ in energy by, okay, they have given one equation where E1 and E2 are the energies of the lower and higher allowed energy states respectively. This expression is commonly known as Bohr's frequency rule. E by h equals delta E by h equals to E2 minus E1 by h. Next, fourth point. The angular momentum of an electron is quantized. In a given stationary state, it can be expressed as an equation. MEVR equals to N into H by 2 pi. N equals to 1, 2, 3 and it goes on. Where ME is the mass of electron, V is the velocity and R is the radius of the orbit in which electron is moving. Thus, an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. That means angular momentum is quantized. Radiation is emitted or observed only when transition of electrons takes place from one quantized value of angular momentum to another. Therefore, Maxwell's electromagnetic theory does not apply here. That is why only certain fixed orbits are allowed. The details regarding the derivation of energies of the stationary states used by Bohr are quite complicated and will be discussed in higher classes. However, according to Bohr's theory for hydrogen atom, first point, the stationary states for electron are numbered. N equals to 1, 2, 3 and goes on. These integral numbers are known as principal quantum numbers. Next, second point. The radii of the stationary states are expressed as Rn equals to n square A0, where A0 equals to 52.9 parts per million. Thus, the radius of the first stationary state called the Bohr orbit is 52.9. Normally, the electron in the hydrogen atom is found in this orbit, that is n equals to 1. As n increases, the value of R will increase. In other words, the electron will be present away from the nucleus. Next, third point. The most important property associated with the electron is the energy of its stationary state. It is given by the expression En equals to minus RH in brackets 1 by n square. N equals to 1, 2, 3 and goes on, where RH is called Rydberg constant and its value is 2.18 into 10 to the power of minus 18 joules. The energy of the lowest state, also called as the ground state, is E1 equals to minus 2.18 into 10 to the power of minus 18 in brackets I by I square equals to minus 2.18 into 10 to the power of minus 18 joules. The energy of the stationary state for n equals to 2 will be E2 equals to minus 2.18 into 10 to the power of minus 8 joules in brackets 1 by 2 square. So overall it comes to minus 0.545 into 10 to the power of minus 18 joules. Next, so here they have given a green box about Niels Bohr. Let's see. Niels Bohr, 1885 to 1962. He is a Danish physicist, received his PhD from the University of Copenhagen in 1911. He then spent a year with J.J. Thomson and Ernest Rutherford in England. In 1913, he returned to Copenhagen, where he remained for the rest of his life. In 1920, he was named director of the Institute of Theoretical Physics. After First World War, Bohr worked energetically for peaceful uses of atomic energy. He received the first Atoms for Peace award in 1957. Bohr was awarded the Nobel Prize in Physics in 1922. Figure 2.11 depicts the energies of different stationary states of energy levels of hydrogen atom. This representation is called an energy level diagram. When the electron is free from the influence of nucleus, the energy is taken as 0. The electron in this situation is associated with the stationary state of principal quantum number and is called as ionized hydrogen atom. N equals to infinity. When the electron is attracted by the nucleus and is present in orbit n, the energy is emitted and its energy is lowered. That is the reason for the presence of negative sign in equation and depicts its stability relative to the reference state of zero energy and n equals to infinity. Next, fourth point. Bohr's theory can also be applied to the ions containing only one electron, similar to that present in hydrogen atom. For example, helium, lithium, beryllium or so on. The energies of the stationary states associated with these kinds of ions, also known as hydrogen-like species, are given by the expression En equals to minus 2.18 into 10 to the power of minus 18 in brackets z square by n square j, and radii by expression Rn equals to 52.9 n square by z pm, where z is the atomic number and has values 2, 3 for the helium and lithium atoms respectively. From the above equations, it is evident that the value of energy becomes more negative and that of radius becomes smaller with increase of z. This means that electron will be tightly bound to the nucleus. Next point, it is also possible to calculate the velocities of electrons moving in these orbits, although the precise equation is not given here. Qualitatively, the magnitude of velocity of electron increases with increase of positive charge on the nucleus and decreases with increase of principal quantum number.